No, no, no. That's maybe we'll wait for 2 more minutes, sir.
Yeah, sure.
2 more minutes, yeah.
No, programs are always the organizer is the chief. We will be ready at time, on time. That's what our normal thing. We will be never late.
No, no. I think we can start now, sir. Yeah.
Yeah, sure. So you can unshare so that I can share.
Yes, sir. Yeah.
Okay. Good evening. Maybe it's a good time to learn maths. So evenings. So is my screen is coming?
Not yet, sir.
Did I go elsewhere? Okay, let me share. I have not shared yet.
Okay, okay.
Is that okay now?
Yes, yes, sir. We can see the screen.
Okay. Now let me show you that the screens are moving today.
Yes, screens are moving.
Okay.
Yes.
In between it stops. It's a technical problem.
Yes.
So I'm excusing myself for the error.
Yeah. No issues, sir. Yeah.
Yeah. Okay. So I hope. So we will continue the lecture. So let me do a quick recap. So what we were trying to, we basically did two examples if you look at it. Okay. So we did the example fx equal to x square and local solvability. That's what we were trying to do it, x square equal to y. And then the corresponding thing what I was telling that we want to prove it inverse function theorem. Probably let me see whether I can reach today, if not the proof, inverse function theorem. We have seen when n equal to 1, this is the result, right? And we have seen that there is a trouble when f prime of 0 is equal to 0. And we have seen that when n equal to 1, when f prime of a is not equal to 0, implies local solvability. Okay. This is what one result we, and this we want to do it for a Rn to Rn, and then what do we replace by your derivative? And that's what you want to introduce the calculus. As you know that if you last 300 years, the development of any mathematics, if you look at it, it is precisely the development of calculus. You have to see how calculus changes the life. If you look at prior to Newton, things were different. But after Newton and Leibniz, after introducing this calculus, the whole science has changed. So whenever you are doing that, that's a basic one-dimensional calculus. But then you have the modern calculus even in the finite dimension and infinite dimension and other kinds of objects. So developing appropriate calculus is what is important. Okay. And the second example, which we have taken very simple. You can, I hope you would have seen some examples. I'm not sure about it. But then we have seen another example when you have an equation in implicit form. The earlier one was an explicit form. Now you have an implicit form, x square plus y square minus 1. So the questions were whether can you represent x in terms of y? Can you solve it uniquely? Or can you solve it y in terms of x? Then This is nothing but the equation of the circle. Okay. Equation of the circle. And what we have seen is that when you have a point here, there is a local solvability. And when the point is here, you see some trouble. But the similar trouble can happen here. The similar troubles can happen all these 4 points. The reason is that all these points, if you compute your f of x is 2x. These 2 points, it is plus or minus 1, 0. That's equal to, not equal to 0. But if you compute your f of y at these points, and then this is equal to 0. So solving y in terms of x is not possible. That's what exactly we have seen it in this example also, right? Even in this example, you have seen it there. Whenever you have a trouble, it's difficult to solve when the boundary. On the other hand, these 2 points, if you calculate these 2 points, then you see, if you compute your f of x, and that points are plus or minus 1, and this is 0. On the other hand, f of y at these points is not equal to 0. So the role of x and y are changed, but the difficulty remains the same. So you see, so what we want to do, and this is corresponding theorem in general setup, is what is implicit function theorem. Essentially, inverse function theorem and implicit function theorem are more or less similar in the sense that if you prove one theorem, the other theorem can be deduced. Even deduction is not that easy, but once you give a proof to one theorem, say inverse function theorem, you can deduce implicit function theorem. Of course, you have to give argument and vice versa. So what we are going to do in the next couple of lectures, we will try to give almost nearly a complete proof for inverse function theorem. Maybe I'll skip in between, because giving a very detailed proof, it may take time. But we essentially tell you what are the things, how to go about it. And that's what expected of such workshops. Not giving all details like what you give it in the university. Anyway, so this is what we were trying to explain to you. And this is the aim of this, mainly these 4 to 5 lectures from my side. So we will generalize, we will give you the precise condition. So what we want to have it is a concept of a derivative. Concept of derivatives. And then you will see that all the time it's not easy to generalize from one dimension. But what I have given yesterday is a direct generalization, what is a directional derivative in all directions. You know the partial derivative, which you have already studied in your +1, +2, but the similar definition can be do, and we introduce what is called a derivative in any direction. Derivative in any direction. Will that be enough? That's the question we are going to see today. Derivative in any direction. So what we have done for the scalar field. Once you understand scalar field, I have taken scalar field not for mathematical technical difficulty. The similar definition I can easily extend to higher dimensions. But then I told you, because the trouble is from the variable, not about the multi-valued map. It is the multi-variable part is more important. Okay, so but then I want to bring up a few things here. Okay, so f is from omega Rn to R, and then what we have defined is that we have defined the derivative of A at any point A in the direction Y. So this is the same concept. I don't want to repeat anything. So you have a point A here, And if you have a direction y given, then these points are of the form a plus hy. So h, when h equal to 0, you get this point, and h varies in a small neighborhood of the origin. It will move points along this direction. Okay, so you are basically restricting your function, a one-dimensional function you are defining along that line. Okay, this is what I have done. Where even though a and keep in mind that a is in omega, this is the multivariable. Y is also y is in Rn, any direction. But then once you fix a and y, this is a function. G is a function from a neighborhood, say some minus epsilon to r. You see, it's a scale. It is a single variable function and scalar valued, and you can talk about the g prime of h. This is what I have done yesterday. And then your f prime of ay is nothing but that is means your derivative of f at the point here and the direction y is nothing but your g prime of 0. This is what we have defined yesterday. Okay, so this is what we are going to do. So the question is that, so we have now defined the derivative in all directions. Will that be enough for you to work it? So you will see that this is not enough. Why that's not enough? And that's what we are going to do. Before that, I want to state one trivial theorem, which you know, as soon as your derivative is defined, one of the first theorem you prove is the mean value theorem. So you can have an analog of mean value theorem for scalar fields. So you have mean value theorem. The proof is direct deduction from one dimension. You can everything because the directional derivative is defined essentially using the derivative of the single value, a scalar value of one variable function. And that's the one you have to use it repeatedly to prove the results for the multi-valued in the scale in this particular situation. So the scalar field multi-value theorem for scalar field. So you just prove it, scalar field. Okay, I will not write the complete statement, but I can exactly tell you. So what I'm trying to say that if you have, these are all vectors. F of, I may not making all assumptions here. So I'm what I mean that you start with the fix A in omega, y in R. Okay. And then assume, so you need these conditions. Assume f is defined in a neighborhood of A. That's enough. Defined in a neighborhood of A. That's all you want it, right? Because these mean value theorems are like a local theorem. It's not a global theorem. So if you want to define a mean value theorem, wherever it is defined, on that part you need it. So what I'm telling is that you have a A. So f is defined in some point here. So you take A, and A plus y may be somewhere here. It has to be, because f is defined in a neighborhood, the A plus y also has to be there. Okay. So what I'm trying to say is that f of A plus y minus f of A is equal to f prime of some point at the point A plus theta y. You recall your one-dimensional case. There exists theta belongs to 0, 1, such that. So you can write down the mean value theorem. So that's what you exactly, you recall fb minus fa is equal to f prime of theta into b minus. Okay. So we are a plus y, you are doing it. Precisely you are trying to say that there is a point here. There is a point there. So a plus theta y will be there. You see? Because theta is between 0 and 1. So a plus, so this is f of a plus y minus f of a will be f prime at this point in the same direction. So you have your mean value theorem. So one more notion I want to introduce here, what is called a direction. There is a slight difference between, I have introduced derivative in the direction y. So derivative in the direction y is not exactly the directional derivative. So the directional derivative is corresponding to the unit vector in that direction. So this distinction you have to know. So every derivative at a point A in direction y need not be the directional derivative. It is the derivative in the direction y, but that's not exactly the directional derivative. You have to normalize it. So this is so these distinctions you have to understand. That's all. Directional derivative. Okay. This is also called Gato derivative. It's a French word. So you have it. So if y is in Rn with the unit vector nu y equal to 1, then f prime of ay in the direction is called the directional derivative. Called the directional derivative. At y in the direction something else came, that's okay. In the direction y. Is that clear to you? Okay. And for general vector y, you define the unit vector and then a y by nu y. That's all. So you have to normalize something is the directional derivative. So we may give a notation when it is a directional derivative. I use it, the derivative of f in the direction y to be a. Okay. So there are two different definitions for giving. So I hope you understood that one. So if you look at it, y equal to a ek, this is the canonical vector in Rn. Then your f prime of a in the direction ek is that is equal to dek. This is your directional derivative in the direction ek, the axis vector of f at a, okay, is nothing but your partial derivative xk. So the directional derivative. So you are looking at this direction. So you see, this is your E1 direction, which is a unit vector. This is your E2 direction. So you get your, so your partial derivatives are nothing but the directional derivative in the coordinate axis directions. Okay. Is that clear so far to you? Now, an important, I want to, important remark I want to make at this stage through an example. I'll define a function f of xy. You would have seen it, but you can construct as many examples as you want it. But then I'm taking one example, xy square by x square plus y power 4. You may think that these are all hard cooked up example. It's not really, but because once you pick up something, you will understand that you can cook up actually not just one example, you can cook up so many examples you want it using that. So that requires some sort of an experience when both xy not equal to 0, 0. That is except at the origin, because at the origin this denominator will vanish. So this definition may not have so much meaning. So at this point you can do it. So these are the two-dimensional computation. So I will not do all the computations. So I want to compute. So you choose a vector b. B is equal to b1, b2. Okay. And then I want to, and your origin is 0, 0. So I'm interested in computing my f prime of 0, this vector at the point B. You can do it, please do this computation. I can just, so what do you do it? You compute your GH. Okay. Okay. That's nothing but, how do you do these computations? F of, okay, A plus HB. So I will just leave these computations. And then you can see that when you compute your GH, you get H is equal to B1, B2 square. Please do this computation. So write down this computation. H B1, B2 square by B1 square plus H2, H square into B2 power 4. So I have done this computation. I kept it. So you do this one. And then your interest is, this is nothing but G prime of 0. This is what you want to compute it. What is G prime of 0? Limit G of H minus, keep this in mind. In your case, this is in my previous notation. If you look at it, this is your A, this is your Y. Since you used X and Y earlier, I'm using different notations. So your A is 0, so you are interested in computing F prime at 0, A, Y. So your A is 0 and B is Y there. So accordingly, you modify. That's it. I used it because they defined the function. Already this variable Y is used there. So GH minus G0 by H, which H tends to 0. You see? But G0 is equal to 0. You can immediately see that from this definition. When G0 is equal to 0 and GH by this new H will go thing, and then H and H will get cancelled. And then when you take limit H tends to 0, this term will get cancelled and one of the B1 will get cancelled, and you will get this is equal to B2 square by B1. And so that means your F prime X is 0, B X is in all directions. This is in all directions, not just one direction, except when the case when B2, B1 equal to 0. So you see all directions. So you take any point, this origin for this vector, you take any B. This is your B1, B2 is equal to B. That's your B. You can take anywhere. You can take anywhere your B. Okay. Direct all the derivative. So here is what, so directional derivative exists in all directions. But unfortunately, f is not a continuous function. This is one point. Maybe my teaching assistants will also unfortunately, this is one point you have to understand. Quite often, suppose you have a function f. So this I want to tell that the continuity, what is the meaning of a function f is continuous at a. So let me just make a remark. This quite often the students makes mistakes in their system. When you say that if a function is continuous at a, you want to check this limit of f of x as x tends to a. But most of the time, when you want to check the continuity at a point a, you try to approximate this function x along straight lines. And then this limit maybe can exist in all directions. But that's not enough to claim that f is continuous. If you want to claim f is continuous, whatever way x can approach in whatever way you like it along the curve. Okay, x can approach to a in any curve, not in just a direction. Then also f of should go to f of a. Okay, then only. So the problem is that when you have a function, this is an example, when you approach f of x in all directions, the continuity may be there along that direction. That does not imply f will have continuity. So one of the culprit is the lack of continuity even after existing the directional derivative, but that is not a feasible thing. You need a concept of derivative which is stronger than continuity. Okay, so for example, if you this function f is not continuous, you can easily see, for example, if I take y is equal to a of x, the previous function, and if I compute my f of x, a of x, you see, not even a, you take a function just y equal to x, you compute. So I am taking this direction. I can take any direction I like it. Okay, I take any direction, and then this will be a square x cube. If you substitute in this one, you substitute in this function y equal to a of x, it is a square x cube by x square plus a power 4 x power 4. So this is equal to a square x by 1 plus a power 4 x square, and this goes to 0. That's nothing but your f of 0, 0 by definition. So it's continuous. So it is approaching along every direction. If you take it, it is going to f of 0. So you have a continuity along that direction. On the other hand, if we take the curve x equal to y square, and if you try to compute f of y square, okay, y, then you can see that this is nothing but y power 4 by y power 4 plus y power 4. That's nothing but half. And this does not tend to 0, which is the value of. So if I approach my point along the curve x equal to y square, you see this function is, so that implies f is not continuous. Okay, so you work out that kind of thing. So the partial, so it's a problem is at the continuity level. So this is exactly happening for the above function. So you have a, the remark is that, existence of the existence of directional derivatives, existence of directional derivatives will not imply the continuity, will not imply the continuity of the function. Continuity of the function. This is not desirable. Okay. This is not desirable. Okay. We need a stronger notion of continuity. Need a stronger notion of derivative. See the trouble, how do you approach mathematics when it is demanded something more than that, right? So now you have to understand the differentiation probably in a different way. How did we define the directional derivative? By taking it as a rate of change. That's a one way of understanding the derivative. But if you go back to the derivative and the way the Newton introduced, yes, indeed it is the rate of change in one dimension, but more than that, the Newton's view of derivative was not just a rate of change. Rather, he wants to understand when a particle is moving along a path, what is my direction? So when a particle is moving along a direction, the particle may be at this position. What would be the direction of that? He wants to know. So that because there are many directions, right? There are many directions at this point. So why do you take tangential direction is my direction? This is what you need a right interpretation. A directional derivative. My direction at any point is nothing but my tangential direction. And that's the process he, in fact, introduced the tangent. Okay. Though the tangent maybe you can introduce in a vague sense, but actual definition, actual understanding of tangential direction is that is defining the derivative. And this is what is called a linearization process. So what you have to understand now, what we are going to do is the linearization process. Linearization. So whenever now for this, so the taking the concept of taking limit is extensively used the one variable concept. Okay, so even when you are defining for the scalar field, when there are multivariable, eventually you are using the one-dimensional nature of it is restricting to it because you have defined a one-dimensional function from there and then take the rate of change. But more than that, you have to understand. So wherever you see in mathematics a concept of derivative, there is a concept of linearization process associated with it. And this is what you have to do it when you do. So let's do it in one dimension, one direction, and then we will define in the higher dimensions your what is called going to have what is your total derivative. So let me go to the next page. N equal to 1 case. Okay. So let's draw the pictures. I don't want to write everything. What is your f prime of x in one dimension? In one dimension, your f prime of x is equal to limit. This is the way you have introduced. I want to see it as a linearization, which all of you know it. So, but I want to define. So f prime of a, f of a plus h. So I want to understand all my linear paths there. Since you have already learned enough linear algebra in the last couple of weeks, of course, you would have studied in MSc and other time, and also you would be teaching it. So let me call this one. Okay, so what is the curve here? So you have a curve here. So let me draw your standard thing which you always teach your students all the time. So you have your point A here, right? And you have your point A. So I'm just recalling what you are doing in your, college students immediately. So you have your this one. This is your f of a, right? That's your f of a. This total is your f of a plus h. This is totally is your f of a plus h. And this is your f of a plus h minus a precise thing. And what is your, so if I call, this is my an error, if I define an error here, EA of h. That's E of h is this one, f of a plus h minus h. So is equal to f of a plus h. Some important concept I want to derive. One, probably you may know it, but quite often it is ignored. F prime of a. So I'm calling your one-dimensional thing. So that's my error I am defining. Okay. So so you have your tangent here. So let me draw the tangent here. So I have my tangent here. So I have this error, right? So this is what you are doing it. And here you will get f of a plus h minus f of a. What do you do it? F of a plus h minus f of a. That's nothing but this one. Okay, so you are making an error. And this is your h. So that's what you are. And but f prime of a, so you will do this one. So you are trying to approximate your f to closer to that one. So what you are basically doing is that you are trying to, knowing f, you want to approximate f of h via my linear map, via my straight line. That's what you are doing to. F of h is this point actually. But what you are trying to do is that f of a, that you know it, and then f prime of a h, right? That's what you are doing. F plus h ea of h. So the total error coming is not just e of h. The error what is coming is this one, r of h. I will make some remark here. So, okay, and this is what you are doing it. This is an exact equation. The only thing I do not know what is E of h exactly. So, so this is a curve, right? So if you look at my curve here, so let me draw one more picture. You would have seen it. So if I look this curve may be my x going to f prime of a. So I am trying to view now f prime of a. So in the normal situation, you are computing your f prime of a as a scalar quantity. But now I am viewing with that scalar quantity as a linear map. So I am trying to view my f prime of a. So every real number given, I can view it as a map from R to R to bring out the ideas and you clear your doubts. So you have f is a function, say from open set Rn. I'm doing it, as I said, for a scalar field. Exactly without trouble, I can do it for a vector field. But once you clear this, it's a thing. Okay, scalar field. And A belongs to omega. Open, this I will take it as an open. If you are not taking it as open, you think that is an interior point because you need a neighborhood to work. That's enough. So you can define any point where it's an interior point. So you get an open set. And with that open set, you can work that. And you know these notations, right? When I write something like BA of R, it is the ball of radius R. So set of all x such that x in omega, such that norm of x minus a less than R. Okay, that's open ball. Geometrically, so far we are using everything. Yeah. So you have a point here. The ball should be here. And this is your R. This is your A. Okay. And so we are working on everything here. So let me define the direction. V is in omega with no, not V is in omega. V be the direction. Let V be a direction. V be V in Rn. So I don't keep on call direction. When a direction means it's also a vector in Rn, such that V is small. So you have to work. So you cannot take no H anymore. So I'm going to have a total derivative. So when I take it out, when I'm taking H, Y, I'm taking only directional derivative. I don't want just directions. I want approximations to happening on all the curves. So I cannot take the direction only HY. I want arbitrary direction. I want my V to go to 0 in arbitrary way rather than a direction. So I will take norm V less than R. So so you will have your A plus V is also in. So you will have that implies these are all setting up. Okay, A plus V is also in BA of R. Correct? Because A plus V minus A is V less than R. So A is here, A plus V is also inside. So here is the definition. Okay, the definition. We say F is differentiable at A. So there is not in any direction. So this is a notation I have set it up. This is a notation I have set it up. Nothing like more than that. Okay, this is the notation. Okay, nothing more than that. Notation. All right. If there exists a linear transformation TA from Rn to R. Linear transformations are defined in the full space. Okay, so the linear transformation R such that F has the representation. So same thing, okay? Or you can write in terms of the norm, which I can do it anyway right now. Representation is called a Taylor representation. So you are basically looking at the Taylor representation. Okay. F of A plus V. So you see, is not on any direction. Arbitrary V plus V equal to F of A plus your TA acting at V plus something more than small order of H. So norm of V into EA of V for vectors V less than R, and both should happen. EA of V should go to 0 as V tends to 0. V tends to 0 in any direction you like it. V tends to 0 means no V tends to 0. That's the definition. So you see here, this is, if you want it, you can call this to be R of V. Together. So this goes to 0 and this goes to 0. It's more than that V. So you have to use this Norm. Norm is nothing but the norm in Rn. You have to do that one. Okay. Then, okay, this is the definition. If such a V exists, if TA exists, okay, TA is called the total derivative this is also called Fresher derivative of f at A, and we don't call it a new notation, we denote it by. So when I say f prime of A is a linear transformation. F prime of A is a linear transformation from Rn to, of course, continuous linear transformation. Okay, linear transformation. Satisfying this inequality. Okay. All right, I think what is the pages are over. I think it's time, maybe it is automatically stopped, looks like yesterday's little bit of trouble. So we will meet after a few minutes, 10 minutes.
Yeah, we will meet after 10 minutes. Yes.
Yeah. Probably it's got stuck today. Now, at least till the lecture is over, it's fine, right?
Oh, it got stuck now?
Yeah, it got stuck at this.
Oh, okay, okay.
I do not know why that's happening again. Okay. Yeah.
Yeah, so we'll take a 10 minutes break and we'll start at 7 then.
Yeah. Yeah, but this is a bit surprising.
Maybe you want to like just shut down your laptop and open it again, or I don't know if that works, or
My only worry,
or maybe just close the this whiteboard and
no, I will start with this. Only my worry is the saving normally done automatically.
okay.
But yeah, I will restart and do it. My only worry is that whatever I have done will go or not without saving.
Okay.
It should automatically save.
Yeah, Nathya ma'am, do you have a question? Someone has raised hand.
Yeah, someone has a question.
Yeah, no, sir. I was about to say that we can start. Unfortunately, the hand is raised up.
Okay.
Thank you.
Maybe I will stop sharing now.
Yes, sir. Yeah.
Okay. Yeah, it is the problem of the draw board. It's happening now.
Okay. It's working now, sir. It's
no, maybe I have to close it.
Okay.
The only problem is that when I close it, it will go or not. Okay, then I will.
Yes, sir. You can also take a short break, sir. Yeah.
Anybody has any questions?
Sir, I have the two questions.
Yeah, tell me.
For what exactly we need the local solubility? Any just one line? We say.
Well, local solubility is, for example, quite often you don't get a global solubility.
Okay.
That's one major issue.
Okay. Okay.
Global solubility is a much more serious issue. You
Like
may have local solutions.
like stability, global stability and local stability.
Yeah, that is a later question. Stability issues are much later.
Okay.
So the question is that can you solve it at least some area?
Okay.
So for example, F equal to B, which I am writing. So for B, A is a solution. So if I make small changes in my, yeah, you can say that. If I make small, you always make error, right? So your problem is to solve maybe for F equal to B. But then suppose I make small changes in B. Can I still get a solution first of all?
Perturbation you're talking about.
Yeah, you can say that. Yes, that's about locally. You are making a small perturbation of the B. Okay. When you make a small perturbation of B, can I get still a solution before you're talking about stability?
Okay.
Then you can talk. So, okay, I say if A equal to B, so for given B, you have a solution that's given. And when you make a small neighborhood, can I get a solution close to it? Say if Y is close to B, do I have a solution before that? You are telling that is that solution close to A? Okay. So the stability comes later after knowing the solution. There is a solution.
Yeah. So when there will be solution, then we can talk on a stability. Otherwise, we can't talk.
Then you cannot even talk on stability.
Yeah.
And many of your PDE problem, integral equations problem, all can be eventually can put it in a infinite dimensional version of what I define now. You can talk about existence of solution. For example, many times when you have one-dimensional derivative and you look for its f prime of A. What is f prime of A? Equal to 0. It's a minimum or maximum point, right? And minimum or maximum point, the derivative vanishes. Okay, so this you may be the minimization is a so if you look at the back for history, most of the time many of the physical problems are looking for solutions which minimizes certain things. For example, if you have a physical system and the physical system, the stability come and energy is minimum. Let me see whether I get time to give an example of infinite dimensional equation. When the energy is minimum, you want to look at the minimal points. Then you would have seen, you can also look into the books. The minimization, you can look the differentiation and the derivative vanishing gives actual physical solutions. And such questions you want to ask later for the higher dimensional and infinite dimensional versions. Yeah.
So the second question is regarding the explicit function and implicit function. So you've taken the circle equation as a implicit function x square plus y square minus 1 equal to 0. So this also we can write y equal to plus minus square root of like.
No, then you are not writing. You are not able to do that globally.
Yeah, that's why I'm asking. So any particular reason the equation can be have the implicit and the explicit?
Yes, many of your things may not come in an explicit form. Many things may not even come in an equation form. The implicit, explicit forms are very rare. Most of your equations will be in implicit form. So you cannot write a circle equation as an explicit equation. But circle and other many objects are important. For example, when the particle is moving like this, you cannot write it as a function. Right? Function has to be certain structure. Suppose a curve is moving like this. How do you write it as a single valued function? You cannot write it as a function. So many things may not come in an explicit form. Sometimes you may not even have an implicit. So many equations may come in an implicit form. You cannot write globally. That also answers your first question. Can you locally, you can view it as a surface. For example, circle cannot be, see circle, you have an intuitive feeling. It's like a one-dimensional object, right?
Yeah.
But then dimension is belongs to, you define only when it is a linear space. A linear space are flat. That's the whole concept, right? There's no curving. But then you have an intuitive feeling of circle is a one-dimensional object. What is this going on? How do you view that one? Mathematically, that you cannot convert it. You cannot have a kind of a mapping from circle to, you cannot flatten it unless you break it. If you cut it, you can break. Cutting is not a topological thing. Okay, so there are issues. Cutting is a kind of discontinuity you are doing it. But on the other hand, if I take a piece of the circle, I can always flatten it by projecting or applying a smooth map on it. This leads to some sort of a concepts called manifolds, which you will not do it here. So the analysis can be developed for manifold. So many of our physical things, for example, our whole nature, whole earth is a sphere. And all our operations are happening on this surface of the sphere, right? And the sphere looks like a two-dimensional object. But then it's not a linear object. It's not a linear space. But then if you take a piece and you cannot convert that into a plane to make it a flat. But on the other hand, if you take a piece of it, I can flatten it. When I say flatten it, it's a kind of a composition of a mapping. I can apply a mapping to it, a flatten. And I can do the analysis by transforming that to a plane. If I take a piece of my surface, I can apply some function to make it flat. And I can do my analysis on the flat, which you know that's a Euclidean structure. And then come back with the same map to that. This is basically you do it in the manifold theory. So it's not that everything is a kind of a explicit form you can do that. In fact, even the important objects, you can't do that. So these are all also related to local solvability. So you are basically trying to solve locally. To make it a piece, you are trying to solve it. You cannot solve it globally, but can I make it a solve locally? But end of it, you may want to get a result globally. Okay, then every point you are trying to do it locally, then you try to patch it up globally. But can we do that patching? There is a very, very important crucial theorem is called partition of unity. You would have seen it somewhere else. One of the most crucial theorem, partition of unity. So there are results which allows you to patch your local results to get global result. You can globally do that. All that is needed when you go to other analysis.
Sir, my last question regarding the direction data. Like suppose we are having a vector xi plus yj plus zk. If you want to know the component along the x-axis, we take a dot product with the I and get x. So that will be the component. Similarly, here in the direction data, when we are talking about the direction data along any vector, so we will take a normal like vector space. We will find a normal at any point. Let a point the p. And we take a dot product with the unit vector of that vector. So now this is not the meaning of component of the normal along that vector, we suppose. This is not a meaning of component of normal.
No, I don't know exactly, but I am saying that wherever you take a dot product, it is exactly the contribution of that vector along that direction.
Yeah, component or no?
It's a contribution of that. It's a force field.
Yeah.
When you have a force acting in some direction, see these coordinate axes are we are designed it, right?
Yep.
It's not the nature is nothing. In a nature, there is no coordinate, right? It's a nature, the force move. So we have a field. Maybe I will make some remark. Maybe it will make it clear during that time.
Yeah.
So when you take a dot product, it gives you the contribution. Suppose you have a gradient vector. And if I take a dot product in y direction, it gives you the if it's a force field, it gives you the contribution of that force in the along that direction. In the normal direction, it may not have anything. That's why the dot product with respect to perpendicular vector is 0. So it may not give you any contribution. So when you have a force is acting in one direction, it will have contributions in all directions. That is given by the dot product. And dot product in the perpendicular direction will be 0. That means this doesn't have any contribution effect.
So same thing we are doing in a direction derivative.
No, directional derivative is just a rate of change.
Okay.
Directional derivative is not taking any dot product. That for one particular example, you got it as a your given function must happen to be your dot product, and which is a linear thing. And hence your directional derivative become the linear operator, same linear operator. Now you see with this definition, it won't change.
But in vector calculus, we take a dot product of the normal with a unit vector of that vector. So there is a dot product with a unit vector.
So that may have some other purpose. Okay.
Okay, sir. Thank you.
Yeah. Shall I now start maybe? Yeah, we already started. We can continue. So I will share now. The thing is working here again. So let's pray God. Yeah, it's moving and nothing is lost. I think this has some advantage so that it automatically saves even if I don't save.
Okay.
So there's nothing is lost. All right. So I'm sure you'll have a lot of questions, and starting asking questions is the beginning of learning. Okay. And these are all some simple, my advice, and never stops ask questions. Whether you get answer on, unless you ask questions, where do you get answer? So keep on asking, don't stop. The moment we stop questions, that's the moment we stop learning. All right. So if Tx is, which you are telling you, and what I was want to tell, yeah. Okay, something I wanted to tell, I don't know, I forgot. Anyway, it will come. Okay, that's not getting delayed. All right. So actually, this was initially introduced by this directional derivatives are introduced in 1908. Okay, by W.H. Young. And then later more general situations, 1911 or something, I think, by Freshe. These are the initial steps. As I said that what I have done is a scalar field. You can actually do it for more general. So let me state a theorem here. This also proves my uniqueness. Everything it is given. This is very interesting. And I will make a remark there. This is basically uniqueness and computation, all contained here. And compute. What are the things you expect? Can you tell me when a total derivative exists? What are the minimum things you expect? Can you tell me? Anyone? You can keep on talking. Assume f is differentiable at a. Anyone can tell me? What do you expect? The first
Continuity.
Continuity, one thing. And other thing, more than that? Something more I have introduced, right?
Direction derivative.
Yes, exactly. So if this is a, we are introduced that total derivative with something stronger than directional derivative. So naturally your directional derivative should exist if f is a function, if f is differentiable at a point. Now I don't write all the time total. When I say f is differentiable, it means its total derivative exists, not directional derivative. Okay, keep that in mind. So I will not be able to be telling that f is differential, total derivative exists. F is differentiable means its total derivative exists. Exactly. So if I prove the directional derivative exists, actually that is more stronger than the continue. You get that one. Can also prove that one. Then for all directions y in Rn, f prime of the directional derivative exists. This is more interesting, and initially you may find little, this is where sometimes also leads to mistakes, that directional derivatives are enough for the total derivative. This is a kind of remark I want to make it. The problem is not the computation of total derivative. Total derivative can be computed using your directional derivative. But what directional derivative does not give the existence of total derivative? But if you know that total derivative exists theoretically, and then directional derivatives are enough to compute your total derivative, you see. So you don't need any other data to compute your total derivative. In fact, your partial derivatives are good enough to compute your total derivative. But the problem is that it exists, you may not know. That error going to zero, you may not know. So that you have to confirm it separately. And we will state a result also. Exists. And TA is determined. That's what I'm saying. TA acting at y, it's a linear transformation, right? From Rn to R. And TA of y is nothing but f prime of a. You see? So you can get your TA of y. TA is a linear, so TA can give completely everything. And one more thing further. So these are all completely your f prime of a of y. Df by dxk, this also you can compute at a by k, where y is equal to y1 etc. yk. Is this clear to you? The statements?
So probably it should be y equal to y1 to yn.
Yeah, sure. It is yn. Okay. Yeah, I think there is a trouble happened again. Something is happening. I don't know. It's a exactly. It's not moving. Something is getting stuck. Some problem here. I don't know. Is it a communication between?
Maybe you can just close it and start again, sir.
Yeah. I don't know why this is for the first time happening.
So if you are using the writing pad, so sometimes the USB cable is disconnected to your writing pad. So power will be not there. So that's why not connected.
Yeah, it's maybe possibly due to that. Okay. Is that okay? Now here it's okay?
Yes, it's yes, sir.
Yeah. Yeah, it's maybe I think it's a problem of the free software. Yeah. So did you understand this theorem quite well?
Yes, sir.
Yes. I think. So you see the existence of total derivative is what's more important. Then it is already telling you that your f prime of ay exists. And once you know this, you can compute your TA fully. And in fact, each f prime of a can be computed in terms of a partial derivative. So the computation of TA is only requires the knowledge of the partial derivative, nothing else. But that is where you so the existence of partial derivatives implies everything, but not guarantee the existence of the total derivative. Please keep this in mind, which we have seen. Existence of directional derivatives are not enough to guarantee the existence of total derivative. The proof is easy. So let me give one proof at least. At least one proof I should give. So let's compute this one. F of a plus b, because a prime exists. That's given to you. Given. So that's what exactly we use it. So this is equal to f of a. This is equal to your TA plus TA of b by definition. Plus norm of E into EA of V. I don't want to write when V is small enough. All that is there. So I will not write, keep on writing that. V is small enough. But if you are giving a proof to your students, be careful to write all the terminologies. But you are teachers, so you let me. So this goes to 0 as V goes to 0. So this is small order of H. I can have this is for any V small, right? For any V, this is not just in one direction, V small. In particular, I can take in particular take V equal to H of Y, where H tends to 0. I can choose that one. Let Y be any direction. I want to know the existence of the directional derivative in the direction Y. Okay, so I can take that one. So if I take in such a way that such that your norm V is equal to modulus of H into norm of Y, this should be less than R. That's how what we have taken that. So a substitute there. So you will get that implies f of a plus hy y minus f of a by h is equal to ta of hy by h plus norm of hy by h into ea of hy. This, what is this quantity? This is linear. So H comes out. So this will become exactly equal to TA of y. Okay. On the other hand, here it's a norm, H comes out. So you may get this is plus or minus norm of y, which is fixed into EA of H1. And this goes to 0 as H tends to 0. Okay. Is that clear? Anything? Anything? So this goes to 0. So that implies, see, this goes to 0. So if I take limit H tends to 0, so that implies f prime of ay, it proves everything together. Ay is equal to limit of H tends to 0 of this guy. I can put that guy here. X is, and that's nothing but equal to TA of y. So you see, so the existence is proved now from that formula. Okay, so that's the first part of the thing. Oh my God. Yeah, maybe tomorrow I should do something new pages. Okay, I learned a trick how to come back. Okay, so X is, and this is nothing but TA of y. Okay. That's it. That's all we want to prove it. In particular, if we take y is equal to sigma yk ek, y equal to yk ek, right? If y is equal to, you can write like that, y1 etc. yk yn, then your y is equal to ek is the canonical basis. Then your TA of y yk is a constant, that is equal to nothing but sigma yk TA of ek. You see, and TA of ek, we already proved by the previous step. This step, TA of y is equal to f prime of a of y. So this is nothing but your f prime at the point A in the canonical direction ek. You see, canonical direction ek. But that is your nothing but your partial derivative. Yk, your df by dxk at the point A. And this is the second part of my theorem. Here. Is any questions in this argument of the proof? Any quick question? Any quick question? Otherwise, I can go and introduce something more. No. Okay, fine. Fine. So it's a simple proof, there is nothing. Now I want to introduce one of the important concept called gradient of a vector field. You know the linear algebra, little bit, gradient vector field. You know the definition, but I want to inform you. I want to see that how it is coming very naturally to your thing. So you have TA equal to f prime of A from Rn to R. And this linear algebra, you would have studied that any linear transformation can be represented by a, what do you know about linear transformations?
Matrix.
Not necessarily matrix, yeah, matrix in the general sense. Okay, and so what kind of matrix? So it's a linear transformation.
Yep.
So can be represented by a, what kind of matrix now?
1 cross n.
Exactly, represented by 1 cross n matrix. And what are the components of that? How do you get that component? So what is that matrix representation? So what is that matrix in the canonical basis? Can you tell me? How do you get a, suppose T is a matrix linear transformation from Rn to Rm, Rm? How do you get this canonical representation?
So the first column is obtained by action of T.
So if you have a linear transformation Rn to Rm, so the matrix representation corresponding to that is nothing but T acting at T1, etc. T acting at En. So this gives you m vectors. So it will be m by n matrix. So if you look at this here, so the matrix representation is nothing but my TA acting at T1 at TA acting at En. But now this is our scalar because we are working with a scalar field. That's all. It's a scalar, and TA acting at T1 is nothing but your df by dx1. You see? And this is called the gradient of f. So the gradient of a given scalar field, okay, is a linear transformation. Is it precisely the matrix representation is representation of its derivative? So that it contains all the information except the continuity of that. So that's why you need to that. It's a gradient of f. There are various notations. Gradient of. This is also denoted by gradient of f. So the gradient of f is your natural with respect to the canonical representation of your derivative, total derivative. Okay. Is that clear to you? So if you look at it here, so your TA of y then is nothing but your gradient of f at that point A at the y. You see, this is what you have so far proved. The linear transformation that you are given. So the scalar field, yeah, this is an important notion. You will see this some properties soon if I have time. But then later you will see two other quantities. Maybe in my colleagues' lectures, you will also see the divergence, other two physical quantities. It's called dive. This is dive of a, so gradient gives you a vector corresponding to a scalar. Okay, and what is that? That's nothing but its total derivative. Essentially, it is the total derivative. What I'm stressing for the last 1 hour is the existence of this just gradient vector is not enough to guarantee the existence of its total derivative. Okay, but then once you know that total derivative exists, gradient contains all your derivative information. You can get your linear transformation, your total derivative from your gradient vector. Okay. And then another two quantities which you will see. So the gradient produces a vector corresponding to a scalar which are familiar to you. Divergence is another operation you will see later. It gives you a scalar corresponding to a vector. And the third one important thing is the curl is producing a vector with respect to that. And you will see what after this inverse simplicity function theorems, the next set of lectures by Purvi, you will see some important fundamental, just like you have fundamental theorem of calculus in one variable, and you will see the various fundamental theorems like divergence theorem, Gauss-Green theorem. You have to see all that are all fundamental theorems in this setup later, involving these operators. That's what exactly you see one-dimensional thing. Integral of a to b f prime of x dr is equal to f prime of b minus f prime of a. Okay. There's also a simple proposition, maybe can the continuity part. Maybe I will since I think if f from omega to Rn is differentiable at A, then f is continuous at A. This is exactly we want to get it, continuous at A. This is much more easy to prove it. Oh my God, something is happening. This keep on happening this today. It's a bit disturbing for you. For me, it's okay, right?
No, sir, it's all right for us.
No, yeah, I don't like it. What's happening? But what? Repeatedly happening shouldn't happen. Anyway, quickly learned something to recover it in a matter of minutes. So, okay. Then differential. I'm not sure whether I'm pressing some button unknowingly. That's maybe possible reason. Okay. I did. Then f is continuous. This is easy to prove. What do you want to show? So you just want to show that f of a plus v goes to f of a as v tends to 0. That's all. V not necessarily any line. So just apply your differentiability. So this is nothing but your TA of v plus norm of v into EA of v. So that's nothing but gradient of f at A v. So you have a formula now. You can use it as and when you require. Plus norm of v EA of v. Right? So if you take a modulus now, you take modulus here, you can take modulus here. This is modulus. This is less than or equal to more gradient at A. This is a fixed quantity, so you don't have to worry. No v. And this is norm of v modulus of E of v. Okay. And this goes to 0. This goes to 0. So that implies f of a plus v goes to f of a. Okay. Yes, I will make maybe a couple of final remarks. I thought I will try to state the inverse function theorem that may not be able to make a thing. So a remark, I'll make a remark here. F prime of a of y is equal to TA of y. That's not grade f at a. Is its dot product. Okay, y. So y is fixed, right? Y is your given direction. So y we will have a direction. This is your a. Okay, and then grade f is also a vector. So you can also grade f may be active. This vector here. And then if this angle is theta, this is just a remark. Another why grade f is so important in physics, and this comes regularly. Okay, so this is equal to something like you are right, modulus of grade f of a. So I assume that y is with the unit vector. Okay, y is also is a similar thing. So this is nothing but your cos theta. So you look at now here. So your this grade f is the theta is the angle between grade f and a thing, and this your thing. And when is this maximum? This is maximum when theta is equal to 0. What does that mean? Which direction? So theta is the angle. Why a is fixed. F is given to you. So the grade f is already fixed. Grade f of a. So you are looking for the derivative in the action of that grade f in various directions. And that has maximum when y has the same direction as grade f. So what it says that the derivative has maximum, okay, derivative. The derivative maximum when y is in the same direction as gradient. Same direction of gradient of fa. Okay, and that's why, so the gradient f is the quantity as the rate of change. I told you, so that this f prime of a of y is the rate of change in the direction of y. Okay, and the rate of change has the largest value when you take the rate of change along the gradient vector. And if it is a normal direction, it will become 0. So there is no contribution. The directional, if theta equal to y, if grade A is perpendicular to y, that implies your f prime of ay, there is no rate of change along the perpendicular direction to gradient. So if you take this gradient of f, so that's why it's so it's pi by 2. And then there is no contribution of your gradient in that direction. Okay. So now I will not prove a theorem, but one of the important theorems I want to state here. So what is we are missing? We thought the continuity is the one we are missing. So can you, so if your total derivative exists, you have seen that your partial derivatives exist, the directional derivatives exist. But when can it have its converse? So because the computable thing is your partial derivatives. or the directional derivative system mode. The other one is a linear transformation. You can give that one. So if the proof is not difficult, though I don't want to spend time here now, but then you apply your mean value. You basically have to apply mean value theorem, which I have stated for your directional derivative suitably to prove this result what I'm giving. So I'm giving the converse part of this one. What are the additional conditions you require to guarantee the existence of even though the existence of the total derivative theorem? Assume all the partial derivatives exist, all the partial derivatives exist and are continuous in some neighborhood BA of R. Okay. Okay. Actually, continuity at A is enough. The existence of the exists in maybe let me state it correctly. Again, exists. I made a strong statement. You don't need that strong. Exists in some neighborhood BAR and continuous at A. The partial derivatives. Okay, all the partial derivatives existence is not enough. You need the so existence of partial derivatives in neighborhood and df by dxi continuous at A. Is that assumption clear to you? So you need to have the existence of partial derivatives in some neighborhood with the continuity at that point n. Okay. Then f is differentiable at A. So it's not very difficult to check it if it exists. Okay. So I don't want to give you a proof, but let me make a remark. Proof, remark I make it. But I'll skip the proof here. See, you know that df by dxi exists given, right? df by dx exists. This is given to you. That means grade df exists. So therefore, by the analysis which I have done so far, the candidate for TA is nothing. Candidate for TA is grade F. So you already have a candidate to verify. Okay, because by uniqueness, it cannot be any other candidate. So if TA, you have to prove that one. This grade F work for that. Essentially, what you have to prove is that want to compute. So you have to basically show that. So the proof to show that basically you compute this one. So you know already the candidate A plus V minus F of A. So you already have the candidate minus grade F at A. Y. So you need to show that this is E of the form norm V into E of Y. That's enough. Showing that's enough. That's where you need to assume the existence of derivative and continuity and apply mean value theorem appropriately to that one. All right. Is that okay? Is that clear? The theorem? Clear?
Yes, sir.
Okay. So the proof, as I said, the proof is not difficult. You try to apply the result properly. So one more important result I want to actually state. These are some of the things which you, when you go with applications, all these results what you have proved in one dimension is required. So another crucial result whenever you deal with calculus is what is called a chain rule. So quite often at the teaching time, we miss these important things. Okay, you most of the time the problem with the students don't get motivated. They stated as a theorem and proof and theorem and proof. The importance of that such theorems are not quite often conveyed. It's important that the why these quantities are important, what are its significance, you have to convey to that. So one dimension, so you do this chain rule or the composition rule, but when you go to and then why do we need such kind of things? Why do you need to have such theorems to prove it? So let me state this chain rule for scalar fields. And probably I will stop it after that. There are a lot of other things to be done, but I will not do it. There are quite I thought initially I will do some applications and some other examples, but then if I start doing that, I may not be able to reach to the what do you call it, my inverse implicit function theorem. So even now I do not know. Maybe I'll get an extra. So in one dimension, what is in one dimension? When n equal to 1, you define, suppose f is a function from R to R. I don't want to state the conditions. And then there is another function. And suppose you define g of t is equal to f of gamma t. Okay. So just recall in from one dimension with appropriate conditions. Okay. I don't want to, I will state it for the general case. F of gamma t, then this one dimension, you know that your g prime of t is equal to, is one dimension case. So if f prime of gamma t into gamma prime of t. You should know that f prime x is gamma x is, gamma has to be composition, it has to be in the correct mapping from A, B to its correct domain, all that to be defined here. So what is in the higher dimension? Now, f is a mapping here. This is in omega, subset of R. And you have a map from to R. This is your scalar field. Okay, this is your F. And then you have a curve. So you have a, you know the definitions of the curve. If you are not clear about the definitions of the curve, you can say that. Curve is a, so you will get a curve here. This is how, it's a continuous map from an interval to that space. So this curve is, you can think that it's a motion of a particle. Okay, that's the way the applications will come that one. A curve is can be then as the path traced by the particle. So you have a curve here, gamma to path here. So that's a gamma t at this point. Okay. So now if I define the composition, so this is a mapping from to R, right? F composition of RT. So you have your GT equal to F composition of T, that's equal to F of gamma T. Okay. So want to know, so this is a mapping. So what is G prime of T? Okay, but what is more important is here, what is actually happening? even though you are computing your G prime of T, it is actually computing if F on gamma T. F can be a force field or something like a scalar field. F may be a physical quantity, scalar quantity associated with the motion of your particle. Okay, and so basically you are computing your rate of change of that physical quantity according to the motion of this particle. That's the way you have to understand. So when I computing G prime of T, it is nothing but the rate of change of F along the curve gamma. Okay, and then that's what the theorem. And so the theorem, so F, assume F gamma G be defined as above. Let T belongs to AB, some interval where gamma prime T exists. Okay. And F is differentiable. The differentiability means total differentiability at gamma T. So to know that F is differentiable at gamma T, then the conclusion is G is differentiable at T, and G prime of T is equal to gradient of F. You see the gradient is coming again. So you take the gradient, so the rate of change of, you see, gamma prime of T. You see this one? This is a, so these are our vectors now. These are vector, this is a vector. Okay. So the rate of change of F is, and this is the tangential direction, this is the gradient direction. You see? Proof is not difficult, so I will leave proof as an exercise. Proof as an exercise. Just apply your, what you do is that, just apply your definition of the T plus H minus T GT. Okay, and then you will get that G of T is F of, so you can just get this is F of gamma of T plus H minus F of gamma T, and just apply properly, something like that. I don't want to do it. It's just 2 line, at least one exercise you can do that one, and you can prove that. And this goes, this you can compute, and then after computing, you just derive. There will be some minor thing, and let me see, at least one or a couple of people will come back and to me tomorrow. Okay, and then compute. Okay, then you will see that where does it go? Compute as H tends to 0. Just put gamma T is equal to A, and then gamma T plus H is equal to, like that. You just put that number and then try to do it. So I think I will stop here. It's a long day, 2 hours. Okay, so I will stop this one, and then we will straight away go to vector field and quickly define. So now that defining for the, I have to define now the fresh derivative or the total derivative for a vector valued function. So, but the major hard work is done already. So instead of a vector, now the representation will be a matrix, and that will lead to your Jacobian. So just like gradient is corresponding to your scalar field, Jacobian is the representation of your linear transformation corresponding to your vector field. So vector field can be considered as each component is a scalar field, and each component will give you a gradient. Put together, you will get your Jacobian. Okay, so I will stop here for today. Any quick questions? Yes. Yes. Hello.
Yeah, please, if there are any questions, please feel free to ask now.
Yes. Or maybe tired after 2 hours.
Yeah, maybe. Yeah, I think tomorrow, I think there might
Not
be
used to listen to the lectures, like teaching is fine for you, right?
Yes, sir. Yeah.
I hope all the participants are listening.
Yes, sir.
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
Yes, sir. Yes, sir.
Yes, sir. We are listening.
Or everybody has gone for lunch or dinner,
No, sir.
rather. Sorry.
No, sir. Everyone is here.
It's okay. No problem. Yeah, we can understand at the hour of 8 o'clock.
Yeah.
You are getting something, or these are all known to you already?
Yeah, some things are new, sir.
Yeah, because unless, yeah, that's why feedback is very important for me. According to a feedback, I can change the level of the talk. I can reduce it, or I can go faster and do more.
So, if possible, can you give some geometric this also, wherever possible?
I was only doing geometry, if I understand correctly. What is the question? Hello?
No, something like when we get a total derivative, is that in 2D when we say
That's what I
2D?
said. Total derivative, I told you it's a gradient.
Yeah.
And gradient is the one where your rate of change is largest.
A greatest rate of increase. Like if you are sitting in a room and one wall temperature is 100. Yeah. Like one wall temperature is 100 degrees centigrade and one wall temperature is 0 degrees centigrade.
Yeah.
And if you are moving straight, so there is no change in your body temperature. So this is the direction of the label surface. If you are directly normally moving to the 100 degrees centigrade wall, you will feel maximum temperature. So this is the direction of gradient, which is normal to the label surface.
Yeah, there are some applications, geometrical applications. I thought I will do it. When you have a temperature moving, there are isothermals and other things. And you can actually see that when the temperature moves, where is the temperature rate, the largest rate of change of the temperature. Okay, so such examples are there, so the heat flow always takes in the direction of the most rapid change. Okay, if you want to understand the heat flow. So heat flow, if you see that the flow of heat, if you mark the heat flow in a thing, it always moves in the rapid rate of change. So it will move along the gradient. And if your other curves are so if you are looking at your constant temperature curve, suppose F equal to constant. Suppose F is a distribution of the temperature, and you mark your constant temperature curve. These are called level curves.
Level surface, sir.
Okay, yeah. Level surfaces. And along the level surfaces, when it is constant, its gradient will be perpendicular.
Always normal to the
level. Okay, when it's normal. And that heat flow takes place along the normal to the level surfaces. That's a physical interpretation in the context of a heat flow. So if it's a temperature distribution, you look at all the curves where the temperatures are constant. Okay, when the temperatures are constant, that means F equal to constant, and then the grade F will be naturally perpendicular to it. And a grade where the heat flow will take place exactly that way. So that way, depending on, so here what we are given is independent of any application.
Yes,
But
sir. Room
according to
example
your-
is very.
Yeah.
This room example is very good way of understanding. Like if you are sitting in a room,
Yes.
like left wall temperature is 0 degrees centigrade and right wall temperature is 100 degrees centigrade. If you are moving normally to the 100 degrees centigrade wall, your body will feel maximum rate of increase in your body temperature. And if you move normally straight like in this way, so there is no change in your body temperature. So this is the direction of the label surface,
Yes,
which
sir.
is actually normal to the this gradient direction is always normal to the label surface.
Yeah. Yeah, gradient is normal to the level surfaces. That's
Level
level
surface,
surfaces
yes,
are
sir.
important.
Yes.
You can have a lot of things in application. You can have the level surfaces are constant energy curves.
Yes, yes, sir.
Okay. So you can have it in different interpretations given. What we are
Yes,
given
sir.
is a very general interpretation because it's a very general definition where we are not using it's a temperature or energy or any other physical quantity. Okay.
Okay, so if there are no questions, I think it's a long day. We will call it a day today, and we will call it a day now, and we'll meet tomorrow for the tutorial sessions.
Yeah, sure. So we can ask, I don't know whether they are attending.
I saw Akanksha is here. She was here just before some time. I think she has left now.
Akanksha and
Pritam was not there. Akanksha was there. Sir, will you be there tomorrow for the tutorial?
I don't think I will be there.
Okay, okay.
They will do it, and if you have more questions, if they want, they will contact me. It doesn't
Okay.
matter. There are
Okay.
plenty of things. They will work out some examples.
Okay,
So
okay.
I don't know what notations they use it. So, but you compare the notations. Any problem is there?
Okay, sure. Yeah.
Since Akanksha attended, so she may know that notation.
Okay, sure, sure. Sir, can you also send me that the PDF of this what you just, I mean, the running notes?
Yeah, that I will do. I can do it. Okay, I can
Okay,
send it
yeah.
to you. Tomorrow it's okay?
Yeah, sure, sir. Yeah.
Okay, then shall I leave?
Yes, sir.
With
Yeah.
your
We will.
permission?
Yes, sir. Yes, sir. Yeah. We will end now. Yeah.